Since we just came back from the spring break, and we need to quickly go over what important things we have learned, like 2 weeks ago, 1 or 2 weeks ago. I will start from this slide because this is the slide we have the transfer function of the governor control system. So we develop the transfer function on how the frequency deviation can change with the change of the load. So the change of load is represented by delta PL here. And we also derive the steady state frequency, which definitely depend on the amount of the change of load. The negative sign here with delta PL just means the direction of load change is opposite to the direction of the frequency change, which means if you increase the load, frequency will decrease. If you decrease the load, frequency will increase. So that load change divided by a factor, which is D plus 1 over R. And later we define this factor as a beta factor, because this one really tell how much frequency is going to be changed if you have any like load change. So we know if you have a bigger D, definitely the frequency deviation will be smaller. Or you have a smaller R. Smaller R means more powerful governor control, more powerful droop control. So simply just a bigger D or smaller R will be better. Okay, better in terms of the steady state frequency. Because the power change of the generator also depend on is based on this droop control. So we can easily derive this formula talking about how the frequency change with the load change. And we use this figure as an analogy to indicate what happened when you have load change. It's like the generator is generating the mechanical power PM, which is powering the load of the system. The load may have a frequency-dependent load and frequency-independent load. So when you disconnect this component, okay, when you disconnect this component, and you are going to lose some amount of load. Definitely, if the system maintains at exactly 60 Hertz, so delta PM will be exactly equal to delta PL. But because the system has frequency-dependent load, so the frequency may change. So if the frequency drop, which means you don't need to decrease that mechanical load, because there will be an amount of load will be compensated by change of the frequency. So we can use this triangle to explain what happened. So the long edge of the top edge of the triangle indicate the total change of the load, and which is equal to two components. One is the change on the mechanical power, and the other is a change on the frequency dependent load. So why there's a negative sign before the delta PD? Because as I said, the frequency change and load and power change actually in the opposite directions. So that's why you need to put a negative sign here. Okay, so this one actually tell a very simple law, which is basically about the power balance. The total change of the load will depend on what will become the change on the mechanical power and also change on the frequency sensitive load. Definitely, you can rewrite this formula to be you put delta PM on the left-hand side. On right-hand side will be delta PL plus delta PD. Okay. So this will give you a better idea. So the left-hand side is total change on the mechanical power. You can measure from the turbine. And right-hand side is total change of the load, including both frequency-dependent and frequency-independent load. So if this system is also connected external area, so you may also need to add another type of load, which may be a tie-line flow. So if this is area 1, there will be some tie-line flow going to area 2. Okay. So in this lecture, we're going to discuss how the frequency change for a system with multiple areas, more than one area, 2 or more area. Then we need to consider the change also is tight line flow. But all the formulas we're going to utilize will be from this slide. Okay, we'll not introduce new formula, but definitely we'll do some derivation for more complex cases with multiple area. Okay, this is the slides we need to review. Okay, this is another slide. The conclusion is because different generator has different droop control, different R value. So at 60 Hertz, which is 1 per unit frequency. So each generator will have determined output. That can be from the economic dispatch, which is optimized result. But if you have frequency deviation, even it's very little frequency change, the generation will change because of droop control. If the frequency doesn't go back to 60 Hertz. So that will give you some new operating point, right? The new operating point may also depend on how much frequency dependent load you have. But anyway, so the new generation among dispatch among the two units or generators will not give you the optimal cost, will not give you the minimal cost. It doesn't represent most economical operation because new generation doesn't meet the original dispatch. So which means if you don't recover frequency back to 60 Hertz, so the actual generation output of the units may be different from your economic dispatch. So you either bring the frequency back to 60 Hertz, then you'll go back to the original optimum point, or you need to better design those R value to make them roughly match the economic dispatch result. Okay. So typically the first one is easier. So just bring the frequency back to 60 Hertz. Another slide is when we study the area with many units, we can always define the total inertia constant and the total droop control factor R. So the total inertia basically does a summation of all the inertia constants of units. And the total equivalent R, basically we can take like a parallel circuit rule. Okay, so which means any R decrease that will reflect it to the total the equivalent R. So if you have one R which is very small, that make maybe the unit number one is very sensitive. That one will take a majority of job to do the frequency regulation. And this formula is still correct. The total frequency deviation in the steady state condition is still equal to the negative change of the load divided by this factor. So this factor we just defined beta factor. A beta factor has unit which is a megawatt per 0.1 Hertz. So why we don't use 1 Hertz, because 1 Hertz is too large to any power system. So 0.1 Hertz is already close to this maybe the stability boundary, not stability boundary, but frequency security boundary. Okay, above 0.1 Hertz, there's some contraction may be taken. Okay. So this value, beta value, can give you the idea on how much load change or generation change can be significant to your system. So in the next slide, which is the last one we showed before the spring break, is this one with the beta values for all the three interconnections. So West connection has beta value 1,600 megawatts. So that is about the significant load or generation change, which can cause 0.1 Hertz deviation. For Eastern connection, that's a 4,000 megawatts. That's pretty large. For Texas connection, Oracle interconnection, that's just 700 megawatts. So 700 megawatts is not large, right? So even the output of some wind farm can be large. Wind farm can close to that. Yeah. Okay. All right, so now we're ready to talk about a system with multiple areas. We start from a two-area system. So here, because we mainly focus on the steady-state frequency, and also we also look into some aspect of the dynamics of frequency regulation. So we don't need to take a very detailed generator models as we develop in the generator modeling section. So here we just simply treat each area as an equivalent generator, and which is each modeled by a voltage source behind some radiance. Okay, so you can consider this this voltage source is like some type of equivalent EMF of the generator, and this radiance like a single radiance. And so the tie line has no resistance. We just ignore any loss on the line. So for this system, you can easily know how to calculate the power flow, right? That's very simple. The active flow from area 1 to area 2 is simply just product of the voltage magnitudes of two EMFs divided by the total radiance, which include the signal radiances of both generator and also the tie line radiance in the middle, then multiplied by sine angle difference. So if you draw the function on how the power is changed, depend on the angle separation, that's basically sine function. So usually the operating point will be somewhere here, far from the 90 degree. So here's a 90 degree. So when angle is equal to 90 degree, that's actually the maximal steady state power you can deliver from one area to another area. So usually the operating region will be far from that limit. So here we assume that one is P120. So if the operating condition doesn't change a lot, always at that initial location, so you can use a straight line to approximate that part of the sine curve. So to solve the slope of that curve, you basically just calculate the derivative of this sine function at that operating point, and that slope is called PS. Okay, so if we solve that, we can approximate the angle deviation in the small area near that operating point by a linear function. Okay, so that power will in the tie line will change linearly with the change on the angle separation. Sometimes we also need to study frequency, because here we want to figure out how the tie line flow can influence the frequency deviation, or how the frequency deviation can influence tie line flow. So we create this formula. So that's very simple, because we know angle is considered integration of frequency deviation. So we simply just divide the frequency deviation, the difference of the frequency deviation by S. S is just Laplace operator. Okay. So this one we can definitely, this formula is good for frequency domain, not for time domain. But later, if we want to derive a transfer function in the frequency domain, we can use this formula. To calculate what PS is, that's basically just very easy. You just calculate derivative of sine function. So I will give you this formula. We are going to use this formula again later in the power system stability sessions on small signal stability and transient stability, because this factor here, we call it synchronizing power coefficient. But remembering, if we use every variable in per unit, okay, so power is also same as torque. So another name for this one is called torque, synchronizing torque coefficient. And basically that depends on we really need power or torque, which one is more convenient for our analysis. So later in the small signal stability study, we're going to utilize TS, which is synchronizing torque coefficient, to describe how to improve the small signal stability. But basically that TS is the same as PS in per unit. Okay. Any question? All right. So now we're ready to study one scenario for this 2-area system. So let's assume there's a load change, which is a delta PL1 in area 1. So here we assume the load change is based on 60 Hertz. So don't ask me whether this delta PL1 is a frequency dependent load or independent load. We don't care. We just assume at 60 Hertz, they're part of system load we measure, and that one is changed. Either it just disconnected, okay, or it's connected to the system at 60 Hertz. So anyway, that load change is measured based on 60 Hertz. So we don't worry about that part is really frequency dependent or independent, or maybe we just treat that one to be just independent, frequency independent load. So when we let this system to evolve, and after some time, eventually the entire system will have the same steady state frequency. So which means you can definitely study the frequency deviation in each individual area or in the entire system. Either way, you will get same steady state frequency. So we can easily write this equation. So if we call the frequency deviation in area 1 or area 2 to be delta omega 1 and delta omega 2, they will basically delta omega. So we don't really need to add that subscript there. We just ignore 1 or 2 because the entire system in steady state condition will be the same. But if you do the dynamic simulation, they can be different, but eventually they will reach the same value. So then these equations came from the power balance equation we have. We simply just add this Thailand flow. Without the last item, the other 3 items have been introduced earlier, right? The left-hand side is delta PM1, which is the power change, mechanical power change in area 1, which is equal to the load change in area 1, plus the frequency sensitive load change in area 1. So if a D1 is 0, there's no frequency sensitive load in area 1, then that part will be 0. But if D1 is not 0, this part will be non-zero. Then the Thailand flow change. Similarly, for the area 2, we have the same equation. We simply, we can just put 0 for delta PL2 because there's no load change in area 2. Second item is same. We just change the D1 by D2. Third item, it will be negative delta P12 because we already defined the direction. It's from 1 to 2. But this, keep in mind, this one is basically equals delta P21. If you want to make the formula be easier to remember, here you need to swap the 1 and the 2. So then the 2 formula will become fully symmetric. Okay. So next we can do one step. So that means the Thailand flow will depend on the power change in area 2 and also the load change in area 2 depend on for the frequency dependent component. Okay, next we haven't utilized the droop control for the governor, so we can have another 2 equations basically that talk about the negative feedback droop control. So now if we study those 4 equations, so those 4 equations has 4 unknowns, right? We have a delta omega, delta P12, delta PM1, delta PM2. But delta PM1, delta PM2 can be easily solved by these 2 formulas if we know the delta omega. So basically, we can eliminate the 2 equations. We only have 2 equations to solve 2 unknowns, which is delta omega and the delta P12. That's exactly what we aim to do for this slide. We want to figure out how the load change can cause the frequency deviation and the Thailand flow change. So next we can, to eliminate the delta PM1, we just simply put the first equation here and second equation there. And then we have 2 equations to solve 2 unknowns. Okay, So then we can draw the block diagram of both areas, then try to connect them. So the formula to connect the two block diagram of two area, two equivalent units will be this formula we derived from the previous slides on the synchronizing power coefficient. By using the synchronizing power coefficient, we can multiply it by the the difference of the speed deviation and also do the integration by this adding this Laplace operator in the denominator. Then we'll get time flow change. So that time flow change will be obtained from here. So this operation basically just calculate the difference between the speed deviation of two areas. And going through this integrator, it will give you the time flow change. And time flow change will go to the first unit and second unit. So pay attention to this sign. So if one is positive, the other has to be negative because we already defined the direction is from 1 to 2. Okay, so then we can combine the two block diagrams for two generators into the same one. Then you can use this one to do some simulation. So later we'll show some dynamic results based on the Simulink of this block. So let's continue solving the delta omega and the delta P12. So it will be this will be the answer. So here to simplify the solution, because we define each parenthesis as the beta, right? So we'll have beta 1 plus beta 2. So from this formula, we tell the speed deviation depend on the negative delta PL1, which is the load change, divided by the total beta factor. So if you only have one unit, right, that will be only just one beta. If you have two units, there will be a two beta. If you have multiple units, they will add up to this denominator. So more frequency dependent load or more governor control, the frequency division will be the smaller the frequency division. So now you understand why the E-synchronization has so very large beta factor, because all the units just added to that beta. And Tesla's synchronization has fewer generator, so the beta factor will be smaller. Okay, continue. We can calculate the time flow change. So time flow change, we're going to use this formula that plug into the delta omega. So it will be this one. But then we do some simplification. We know the time flow basically just equal to the frequency division multiplied by the beta factor of area 2. Okay. Then this will be the formula to calculate the time flow. So now we have the formulas to calculate delta omega and the delta P12, and we can use one example from Sadat book. So that gave you some more realistic numbers you can try and to calculate. I don't go through the detail. Basically, just gave you all the parameter of the block diagram from the previous slide. So you can use the formula. This is the formula we derived, right? You can use this formula to calculate the frequency deviation by plugging in the load change, the R value, and the D value. And finally, because this is the load increase, the final frequency deviation will be negative 0.005 per unit. Multiply this value by 60, you will translate this value into the unit of hertz, which will be negative 0.3 hertz. So new frequency will be 59.7 hertz. So then using the droop control formula, you can calculate the delta PM1 and the delta PM2. So generator 1 will increase the power by 0.1 per unit, which is 100 megawatt. Unit 2 will increase by 0.08 per unit, which is 80 megawatt. And time flow change will be negative 84.5 megawatt. Okay. Okay, so if you do a simple math, for this case, the load change is 187.5 megawatt in the area 1. And the total generation change is 180 megawatt. So which means the generation didn't increase to the same as much as the load change. Why? Because you have a frequency deviation. So because system has frequency dependent load, it doesn't need to change that much. So using the Simulink, if you find that example and also the file, you can run the Simulink. It will give you this simulation result. The first chart indicates how the frequency deviation will change. And you see eventually they will get pretty close. So that value is negative 0.05 per unit, same as our calculation. The second chart indicates how the mechanical power and how the Thailand flow will change through some dynamic process. If you check the ending value, that's basically same as what we calculate here through some dynamic. Okay, so this is the 2 area. Any question? Next, we're going to generalize that study into a multiple areas case. So if you pick any area, that area has some total generation, which is PMI. If we call this area number I, so PMI will be total generation. So delta PMI will be change on the generation. So load will be the PLI, and delta PLI will be the change on the load. And also we assume this area has some frequency sensitive load with factor DI. So that DI multiplied by final frequency deviation will tell you the change on the load due to the frequency change. And also this area will be connected with some neighboring area. So there will be some other area. I just didn't draw it here, but that total power leaving from this area to all the neighbors will be delta PI. Okay, so which can be calculated based on the summation of all the Thailand flow. But here we pay attention to the subscripts ij. We assume all the flow is coming from this area to the rest of the system. Okay, so it will be the Thailand flow leaving this area. So all the analysis we have done for the 2 area case will be can still be applied to this case. So we start from this equation about the balance of power. The total generation is equal to the total change on the Thailand flow, total load change, and also the frequency sensitive load change. And we also add the 2 formulas with the frequency droop control of the governor and also the frequency sensitive load. Then we know the total change on the Thailand flow leaving from this area can be calculated by this formula. This is basically the same formula as from the previous slides. For instance, that is basically a generalization of this formula when we consider multiple area. So we still can define everything in this parentheses as beta factor. And the next equation is when we model the entire system, if we consider all the area will have some change on the Thailand flow going to the neighbors. When we add all such a change on Thailand flow together, that has to be 0. Because some change can be positive, some change can be negative, but eventually there's no additional location or place for all the flow to go, right? So eventually that has to be 0. So for instance, if there's only 2 areas, so the flow leaving the area 1 will be P12. The flow leaving the area 2 will be P21, right? P12 equals P21. So the sum will be 0 because P12 has to be opposite or negative P21. Okay, so this is just a more general case to help for the balance through the entire system. Then you can easily conclude this formula. So in this formula, the numerator will be total change of the of all loads of all area. So if right now it's not just a area, one area having the change of load, you have a load change here or there. So you just calculate the total change on the load and divided by the sum of all the beta factors, which is the beta factor of the entire system. So that will tell you the frequency deviation. Then you can calculate the time flow, which will be this formula. So this is also similar to the formula we derived for the time flow change. So if we check whether those two general formulas can apply to that two area case, for two areas we can just assume that delta PL1 is non-zero and delta PL2 is 0. It's same as the example 12.4, and this is exactly the same formula we have. Okay, so which means those two formulas are verified. Okay, so if you need to solve the time flow change on each individual time line between any two areas, the first formula is good. That gives you the steady state frequency. When you use the second formula, this formula only tells you the total flow change of all the time line connected to this area. It doesn't tell you the flow change on each individual time line. So you still need to calculate such a total flow change for each area, and then you maybe do some math, very simple math, to figure out how much each time line can change. All right, from those examples, we know when there's any load change in the system, eventually there will be some frequency deviation, which is taught by this formula. Okay, so if you have a bigger D or smaller R, or you have many generators, so all the generator will have some droop control. We'll introduce some R, which is like you have a circuit with many parallel branches. So those many parallel branches together will give you smaller total impedance. So then that can help reduce your delta omega. So more beta values, bigger beta value, or which means bigger D or smaller R will give you smaller frequency deviation. But based on this simple law, if this one is non-zero, so this one will be never zero. It can be very close to zero, but it will never be zero. And also we know we cannot make R to be too small because that can cause some stability issues. It only can reduce the steady state frequency, but it doesn't guarantee your entire closed loop control system to be stable, right? Based on what we have tried, based on the Locker's method and Ross table, we know there's some stability limit. So then we need to talk about the limitations of a Gardner control system. So Gardner control does not recover frequency back to the scheduled value. So if it starts from 60 Hertz, any load change will deviate the frequency from 60 Hertz. By using the Gardner control, there's no way you can go back to 60 Hertz. Why? Because the Gardner control is based on it's basically a proportional controller, based on the droop control. The droop control, the idea is you need to have some deviation. Then you just use that deviation to multiply by some gain, and use the value to change the valve opening. But if you have no deviation, there's no control. Okay, so deviation has to be there. And the Gardner control does not adequately account for the cost of power production, which means if you start from economic dispatch for the entire system at 60 Hertz, as long as there's any load change or generation change, all the unit will operate at the new condition, which is different from original dispatch. So governor control serves as a primary means of frequency regulation, but it's not suited for fine frequency adjustment for a large system. Okay, so there's also some other limits. So if you read the section 4.3 in the April tutorial, so there's many discussions. Here I just list some of them. The first one is the spanning reserve is not considered. Spanning reserve means the room for your current generation to the limit of the generation. That's called spanning reserve. So which means if one generator is generating 100 megawatt power, but if you try to keep increasing the power before it reach any security or stability limit, maybe the limit is 150 megawatt. So which means that 50 megawatt will be the spanning reserve. Because this unit is spanning, and also there's amount of reserve, so you can generate more. That's why it's called spanning reserve. There's another type of reserve, which is non-spanning reserve. Non-spanning reserve means the unit is not spanning, but if you need it, it can be started quickly to become reserve. For instance, you have another gas turbine unit, which can easily generate another megawatt, 50 megawatt power, but now it's off. If you need it, you can maybe take a few minutes to start it, and they will give you another 50 megawatt. But that unit is not spanning, it's not spanning reserve. So when we say spanning reserve, we really mean the current generation, the room from the current generation to really the security limit of the unit. When you integrate all such rooms together for all the generators, that gives you the total spanning reserve of your system. The spanning reserve is very important. Especially for future system, you have a lot of renewables, because renewables has some uncertainties. If you, for instance, if there's a tornado moving towards the direction of some wind farm, so you have to shut down some unit, or maybe some cloud moving on top of the solar farm. So the generation from renewable energy can be quickly changed. So you need to have some reserve. Non-spanning reserve may not be that responsive. You have to use spanning reserve to easily just increase the generation. If you have a governor or you have some other control, you can quickly just increase the output. But the limitation with governor control is, so far we haven't modeled this spanning reserve. Right? There's nowhere we have considered this spanning reserve in our existing formulas or block diagram or models. Definitely we need to add this one to governor control. Second is, so each governor in practice has a dead band. Typically it will be 30 to 40 millihertz. Even you set up the governor to recover the frequency back to 60 hertz as close as possible. But it still has some dead band, which means when the frequency fall into that very narrow range, like a 59.97 to 60.03 hertz, the governor doesn't respond. And the responses from different type of units can be different. Like hydro units can be very responsive because hydro units is based on the principle to change the mechanical energy carried by water to become electric energy, right? That can be easily done through the turbine. But combustion turbine, steam turbine, they can be slower. They may or may not be responsive. We haven't considered type of units in our existing formulation. And the governor control can be blocked if any operator of the power plant they try to protect this unit, or they see this unit become somehow unstable. They can intentionally block these governors for a certain amount of time. Maybe when the system is experiencing a large disturbance, or maybe when the system is in the restoration process, they can intentionally block some governors. Okay, so the main question is, when you model this entire area as the equivalent unit to study the frequency, the total frequency, you don't have the detailed information as listed here, right? You only have roughly the total inertia and the D factor, R factor, then you do the calculation. So we definitely need a better control to allow us to adjust the frequency more accurately. Based on the studies on the Eastern connection, Western connection from 2011 to 2013, 70 to 80% of units are modeled with governor, which means if you look into the dynamic model, you do see the governor model, you see the R value there, right? So which means there's some kind of droop control there. But only 30 to 50% of units actually have governor responses. Well, the governors of others are either turned off or inactive, which there's two scenarios. The first one is when the NERC create the model for EI, WCC, or Texas, they ask all the utility companies or ISO, they just report the most accurate model for their generators. When they model the generator, they do have governor. The governor is already installed. They also can check the value of R value, okay? And when they report everything to NERC, and NERC, there's a working group, which is MMWG working group to create the model for the entire intersection. So they have to assume the governor is there, but actually they don't know whether this operator, they just intentionally turn off that governor just for safety or security concern for that generator. They don't know. They have to consider the most optimistic scenario, which is all the governor is actually online. But in reality, they found out that only like 30 or 50% of units, they actually respond to the frequency deviation. One reason is because some governor is simply not functioning at all due to some reason. Another reason is there's some dead band. They can set up a bigger dead band. So that makes those units to be less responsive to the frequency deviation. Okay. So due to those so many limitations, we do need to have another control which can safely bring the frequency back to 6 Hz if we really want. That is called automatic generation control. If we first draw that the block diagram for 2 generators or multiple generators, we know by using the droop control of each generator, we cannot recover the frequency deviation back to 0. Then we can add a new controller. So this new controller is simply just still a negative feedback, but it will be multiplied by Ki divided by S. S is 1 over S is just an integral controller. So Ki is just an integral gain. So this is like an integral controller added to 1 unit. So here I only just assume this one to be added to just 1 unit, not all of them, right? So you don't really need to have every unit to be in the automatic generation control, but they just give you a additional control for fine tuning of the frequency. So this control will directly change the setting point. Like for instance, for this unit, it has setting point that can be constant, but the other unit, that setting point will be changed by this integral controller. So the input of this integral controller will be the frequency deviation. As long as the frequency deviation is not 0, this one will be integrated, multiplied by Ki, and then will be used to change the setting point, which means as long as frequency doesn't go back to 60 Hz, this controller will be functioning. Because the system load can change all the time, the generator output must be adjusted automatically. So this one doesn't need any operation of the people, a human. So it just put a selected unit into this automatic generation control, and by feeding the frequency deviation signal, and it will gradually change the output of the unit and finally bring the frequency back. So the objectives of the automatic generation controls include the first one is still low frequency control. So this is a primary objective. Okay, so you can just regulate the frequency back to 60 Hertz or maintain the power exchange between the areas. It can also help on the generation dispatch. That's a secondary objective because you can use this control to redispatch the generations among the generators in order to minimize the operation control. For instance, if you do the economic dispatch, usually it can be done every like 3 to 5 minutes based on the operating conditions, or maybe at a longer time frame based on to give you the most economical cost. But when the system is experiencing some disturbance or new conditions, if you have multiple units connected to the AGC, you can use that unit. First, you can bring the frequency back to 60 Hertz, so that you can recover back to the dispatch result. And you can also use the AGC to influence maybe some of the unit maybe which can help to reduce the operation cost. So that can give you more flexibility. During a lot of disturbance or some emergency condition, the AGC is bypassed because under a lot of disturbance, you have some risk to become instability, and so to ensure the system, the stability is the most important thing. So AGC usually can be bypassed, and you can utilize some other emergency control to recover frequency. So at the end of this section, we'll talk about some other control methods, such as end-frequency load shedding. So there are multiple levels of control. So under emergencies, you need to do very large amount of generation or load control to bring the system close to the safe range, secure range, and then use the governor to bring the frequency back to some very narrow area near 60 Hertz. Then use AGC to really bring back to 60 Hertz. I think we showed that the figure before, right? There's a, let me see. Okay, yeah, we see a similar figure in the generation section. Maybe, yeah, we'll talk about that later when we see a big picture about frequency dynamic during a large events. So how do we model AGC? First, let's just assume we use the AGC just for isolated power system, which can be modeled by this plot diagram. We simply just add the outer loop, which is an integral controller. When we rederive the transfer function from the load change to frequency deviation, and in this feedback, we have added this one component, right? So if that Ki is equal to 0, this one will go back to original droop control. If we write down the transfer function, the transfer function will be this one. So that Ki is added here. So if Ki is 0, let's say if this one is 0, this S, and this S will be canceled. So you can just eliminate this S, eliminate this S, and this one will become 1. And then this one, when you plug in 0 to S for infinite time, this one has to be non-zero. This one cannot be 0. But now, if Ki is not 0, no matter what value we take, when you plug in 0 to S, 0 or 0, anywhere. So what you're going to get will be 0 divided by non-zero. Okay, so this one can be 0. So which means the frequency division with this integral controller will be 0. Definitely, if you can safely or stably go to that final steady state condition, then that frequency division will be 0. But if you control system loses stability, that's another story. Okay. So in this example, you can use Simulink to study the dynamics by letting the Ki be 7. You can see the frequency division will finally go back to 0. All right, so now we can consider the ADC with a multi-area system, and we study how to utilize the ADC to control the frequency division of the entire system and also Thailand flow. We still use this model for each area. The objective is just to restore the generation load balance in each area. Let's assume very simple control strategy. So in this strategy, we keep the frequency approximately at 60 Hz. That's our goal for the ADC control. And we want to maintain Thailand flow close to the schedule value before any disturbance. And we want to ensure each area to absorb its own load change. Okay, so without any disturbance, if we measure Thailand flow and put in all the value into the table, and after any disturbance, as long as the disturbance is not large and propagating to the entire system, eventually we hope the frequency is still at 60 Hz. And when we measure Thailand flows, each Thailand flow is exactly, or at least very close to the original Thailand flow in the table. And then when we look into what happened in each area, we found out, okay, so if this area has load change, then the local generation will take care of that load change. Okay, that's a very simple control strategy. Even it may not be 100% practical, but this is very easy, very fair control strategy. To implement this strategy, we have to introduce one index, which is the area control error. It is just supplementary control signal added to the primary low frequency control through an integral controller. This integral controller will be ADC. So it can be some program, right, implemented or deployed at the control room of the system. It will collect the measurement data from multiple locations and calculate this index and give this index to the generator units connected to this automatic generator control. Then it will take care of that control strategy, simple control strategy. So here we assume this this control index will be a linear combination of the Thailand flows and also frequency division, right? And we introduce a weight, which is B. So first item, so first of all, the unit of this index is in power. First item is just tell the total Thailand flow change from this area. We just add the change of each Thailand connected to this area, and the total will tell how much total flow change increase or decrease from this area to the neighbors. And the second item is the frequency. So we multiply by B and to translate this value into some power. So this, we call this this weight or this coefficient as frequency bias factor. So you can immediately recognize this B factor is very like a beta factor, because earlier we utilized the beta factor multiplied by frequency division, we can translate into a Thailand flow change. That's for the cases we only have a governor without ADC. But right now, with ADC, this ACE is what we define. You can arbitrarily define this one. Beta is also the value given by you. You can give any beta value, so which means You can either take a beta value or take a totally different value. That's totally up to you. In our next few slides, we'll try to do a study to figure out what if we take a value same or different from the beta. So what's going to happen? So any combination of ECEs containing the delta Pij or delta omega will eventually result in steady-state restoration of the tight line flow and frequency division. So what does that mean? That means you can control ADC system, okay? In the ADC system, you define this area control arrow. And this arrow is for each area. And you give this signal to some of the generator connected to the ADC. Because that ADC controller is an integral controller. As long as this area is non-zero, that integral controller will keep working to change the generation. They only stop working when then this area becomes zero. So when this area becomes zero, the frequency has to be same, original frequency. Tight line flow has to be original tight line flow. This is about steady state. The condition in the system can be safely go back to reach the new operating condition. Okay. Because this is an integral control. And what combination of ACE signals should be selected is more important for dynamic performance condition. What does this one mean? So as long as you include some tight lines, frequency division into the ACE for some unit connected to the AGC, that tight line flow frequency will recover back to the original value. But how quickly they recover or how stably they recover really depend on that beta factor or B factor. If you select different B factor, some control will have better performance. That's what we need to study. That's more from a dynamic performance consideration, not from the steady state consideration. Any question? All right. So in practice, we don't need to make every unit to be in the AGC, only just the selected unit to be in AGC. But let's assume very extreme case. I have an entire ECE connection, fully connected. I only gave one generator AGC. And now there's a load increase, sudden load increase. Then that generator will, first the governor will because we have frequency dependent load, we have D, we have R. The load trend divided by D plus 1 over R for the entire system will translate to how much frequency will change, right? That frequency will go to that generator with AGC. So that will, because of the feedback control, if the frequency is negative, which means division is negative, it need to increase the generation. It will keep increasing, and then after the control loop, which is like maybe from the previous slides. So eventually that the unit will increase the generation. Finally, the frequency will go back to 60 Hertz, as long as that unit has enough spinning reserve. If we only have 50 megawatt spinning reserve, but the load change is 100, it will never go back to 60 Hertz. As long as you have enough units connected to ADC, their total spinning reserve is more than the load change, you'll be safe, okay? Another opposite scenario will be you suddenly decrease the load. You just disconnect maybe one substation with 100 megawatt. And this unit is in AGC, so it will decrease the output, right, by 100 megawatt. But in some cases, maybe it has some lower limit. It cannot decrease by 100 megawatt. Then it will just stop there. The frequency cannot go back to 60 Hertz. You need to have some other unit give you that room. So each generator connected to the governor and AGC will have some upper limit and lower limit. As long as the upper room and lower room will be large enough to cover the load change. Even you only have one unit in the AGC, eventually the system will go back to 60 Hertz. But how much time it need to take to go back to 60 Hertz, that's the question. It can be very bad. It could take a very long time. So meanwhile, you may have some other violation. So that's another concern. Okay, but for ADC, as long as the system can have steady state performance, they will go back to 6 hertz. Yeah, we stop here and we'll continue on Thursday.